these lectures. So the aim of these notes is to actually kind of bird's view overarching issues on machine learning. And there's a brief review of programming with Python. So these introductory slides, they're going to have a quick reminder on Python programming and libraries, which you will find very, very useful. There's also a reminder on statistics. So we will not cover everything here because we want to get up to speed. So we're going to give you in the first part of this first lecture today, we're going to have a introduction and review of some specific topics which you may find useful. If we now move on, we are going to, in the next lecture, we're actually going to look at linear regression, so which is actually a plain linear algebra based method, but you can also derive it from a statistics approach. So we are coming back to some of these things. After that, which is tomorrow, we are going to look at the logistic regression. We are going to move into methods which many of you may have heard of, like decision trees, random forests, and widely popular methods like boosting. So there's a library which is called extreme gradient boosting, which is actually one of these libraries which wins many of these competitions when it comes to classifying data or fitting a specific function. Then we are going to dive into, on Thursday, into the mathematics and applications of neural networks and deep learning methods. So that's going to prepare us for the analysis of data. The data which we are going to look at, we will mainly deal with them with more advanced methods than those which we will cover the first 4 days. But these first 4 days will, in a way, serve as a way to set the scene on what are the essential aspects, how do we understand the methods, how can we use them, what are the pros and cons of different methods. Then we're going to dive into convolutional, recurrent neural networks. We're going to look at generative models and reinforcement learning. And the emphasis, as I said in the beginning now, the emphasis will be on 2 types of nuclear physics experiments. And one is actually on recognizing events from beta decay experiments. And Sean Liddick is going to talk about that. And then we have how to analyze data from active target experiments. And that's Danielle Bazin, who's going to talk about that next week. So Sean is going to describe how to analyze and how to understand the physics of beta decay experiments. And I hope you can forgive us, but within 2 weeks only, there's obviously a limit to how much we can cover. So we've decided to focus on these 2 types of experiments. And one of the things which you will see after we've done with some of these very, very simple cases of data, like the reading in nuclear binding energies, is that one of the big difficulties is actually setting up your data in a meaningful way so as it can be used in a machine learning algorithm. So these are the basic topics which we will cover. When we look at machine learning, we just wanted to give you a very, very quick overview before we move on to some applications now. Ideally, machine learning actually represents the science of giving computers the ability to learn without being explicitly programmed. There is actually a human who at the end writes the program. And with the methods which we're going to start with, like linear regression and logistic regression, they are pretty deterministic algorithms. There's not much machine learning. Actually, you have even analytical equations for the unknown parameters or so-called estimators of the model. So one of the things you should keep in mind is that at the end, there is always some human in most of the things we're developing, which actually ends up writing the algorithms and setting up the insights and the knowledge about a specific problem. Like in physics, you have specific problems like energy conservation, momentum conservations. And these are aspects which you need to plug in your favorite algorithm. The machine learning is an extremely rich field. You can, in half jokingly, say that if you can spell it correctly, you have almost a feeling that you will get a job in the software industry. It's a field which is rapidly evolving, and sometimes you have this feeling that you can barely stay ahead of new developments. There are popular libraries written in Python or in C++ or other languages. So Python can often be used as a kind of interface between the user's endpoint and the link with these different softwares. So we have a widely popular library. Released in 2015, it's TensorFlow library for deep learning. Facebook has a PyTorch. Keras is a wrapper on top of TensorFlow, which makes life a little bit easier to use TensorFlow. And if you peep into their GitHub sites, you will see that these are communities which have thousands of developers. And the number of developers actually keeps increasing. It's a multidisciplinary approach. There's a huge room for experimenting and trial and error. And clearly that leads to redefining some of the mathematics. Some of the methods are very intuitive, like decision trees. There's not much deep mathematics behind it. Other methods have still lots of mathematical proofs which are left there for you to develop. And in a certain sense, it's a field which requires that you have a good understanding of things like statistical data analysis, probability theory, some linear algebra elements, and many other topics from mathematics and statistics, in addition to being able to program. Now, I'm going to launch a small poll here, so which you can answer while I talk. And this is a little bit, we want to see what your familiarity is. So you can probably see the poll here now. And if you could just click on whether you feel you're confident with Python programming, if you've been using IDEs like Anaconda. So an IDE is an integrated development environment. Whether you're familiar with machine learning libraries like TensorFlow or things like that, scikit-learn, PyTorch, or whether you're familiar with Jupyter Notebooks, because we are going to run pretty many Jupyter Notebooks here. So I see the answers are streaming in. Thanks to you folks. So let's continue. And if you have questions, I mean, please chip in and ask them or raise your hands. What we want as kind of learning outcomes here is to give an overview of some of the central aspects of these algorithms, which are used in machine learning. And as I said, we will bring in several of the algorithms, some of the most used ones. And more specifically, what we want is to teach a little bit about basic data analysis, data optimization, machine learning. You should be able, when you're done with the course, to actually apply this to other types of systems or your type of data. We want you to have an understanding of some of the central algorithms which are being used so that you see the pros and cons. And don't be disappointed if you realize that at a certain point, there are actually many parameters which are normally fine-tuned. So the methods we will focus on, as we said, is linear logistic regression. So linear regression is typically used for you fitting a continuous function. Logistic regression is a typical classification method. So if you have an event with something like a yes and no, 1, 0, and so on, typical binary types of events, or if you have more types of events, you would use linear logistic regression. You can use many of the other methods. Basically, all these methods can be applied to both a classification and fitting some continuous functions which you would like to have fit. And then we're going to work on some specific examples. And the exercises we are going to have today are more simpler ones. I mean, just to have you get you started. And the same with those on Tuesday and Wednesday. On Thursday, on the other hand, we're actually going to look at data from nuclear physics experiments conducted at Michigan State University. And these will be linked up with Sean Liddick's lectures on Friday. The types of machine learning. So we would typically distinguish normally between something which is called supervised learning. So that means that your data are labeled. So there's somebody who's actually looked at your data and they've written whether this could be a benign tumor or not a benign tumor. It could be a yes and no case and so on. So the data are typically labeled. And that's often cases where the data set is smaller because it becomes expensive to label all data. When we, on the other hand, look at unsupervised learning, this would be situations where we would have tons of data and it would become way too difficult to actually sit down there and label all the possible events. So you would like then, if you have terabytes or even petabytes of data, it's becoming more and more common in physics now. So if you have terabytes of data, then typically unsupervised learning methods for finding patterns and relationships in the data sets are actually things which we will be looking after. Some of the typical common tasks, there would be classification. So you would have 2 or more classes. So one of the cases we're going to look at when we develop our own codes for neural networks is actually to look at the classification of handwritten numbers. So the goal then is typical to produce a model that assigns inputs into one of these classes. An example is to identify digits based on pictures of handwritten ones. So classification often ends up being a supervised learning case. And we will see examples of that. Then we have regression, which is finding some kind of functional relationship. So you have a model and you want to use that one to fit a function to your data. And typically then the goal is to construct a function that maps input data to some kind of continuous output. We have clustering, so data divided into groups with certain common traits without knowing the different groups beforehand. And this is often a very common thing you would encounter when you're looking at unsupervised learning. Let's look at some of the essential elements of machine learning. So the methods which we are going to cover, there are 3 central ingredients. And we are going to train you in the understanding of these central ingredients. And these are ingredients which you will deal with, irrespective of whether you do unsupervised or supervised learning. So obviously one thing is your data set. And it's typical to divide your data set into some training, which you use to fit a model. You can have some validation. We're going to be a little bit lazy in the course here. So we're going to just split our data into training and test data. So it means that we would use some of the data we have to train a model, and then we would apply the model on some data which was left out. And actually to take your data and turn that one into or the machine learning algorithms is something which many people actually find as the most difficult part. And we will see how to do that in more detail on Thursday. In the beginning, we are going to look at some vanilla cases where most of the cases we are going to look at then are cases where it's very easy to see how we set up the data. So data is one ingredient and you can't live without it. Now, the next thing which we need, and that's another thing which is often a difficult thing, is actually the choice of model. So we need actually to develop a model, to have a model which reflects our insights and the basic knowledge of a specific system. So we could, for instance, know that the data has a specific behavior, which leads to you making up a model, which is a polynomial. Then finally, the thing which we need is to define a way to gauge whether the model is a good one or bad one. And that leads to something which is called a cost or /loss function, or some people will call it the error function or the objective function. So there are many names here. I'm going to stay with cost/loss function. And that is a function where we typically, which we typically use to assess the quality of the model. So these are the three basic ingredients. So you have your data set, you have your model, and then you have a way to assess whether this is a good or bad model. Now, at the end, at the heart of basically all algorithms, perhaps except for the standard linear regression, which we are going to look at pretty soon, we do actually have to call some minimization optimization algorithm to find the optimal parameters or estimators which describe the best possible way of data. And that leads to a multi-dimensional function normally, because we will have tons of data to fit. And we will have tons of parameters. If you're dealing with neural networks, we will have pretty many parameters which need to be fitted. And that leads into the field of minimization optimization. And there's a whole class of methods. The typical ones which we are going to meet are so-called gradient methods, which allow us to find the minimum of a function of a set of parameters. And this is often the, how to say, the hard work which machine learning algorithms are doing. So we have the data, we have a model which we're setting up, we have the function which we use to assess the quality of the model, and then at the heart of everything, we have a minimization problem to solve. So these are some of the basic ingredients when we're doing machine learning. The other thing which I would like you to think a little bit about is about some of the phrases which you see here. So when we think of machine learning, statistical analysis and things like that, we often have words like predictions, estimations, correlations, and causations. And the question is, what do you think about that? I mean, what do these words actually mean to you? So when you have correlations, then normally you would typically say that if A is correlated with B, then B would typically be correlated with A. Whereas causation, on the other hand, is something which is directional. So you could say that A causes B, but you wouldn't say that B would lead to A. So these concepts actually, in some sense, what makes a difference between machine learning and statistics. So machine learning is about predictions and finding correlations in your data. So predictions means that you want to develop a model which allows you to make a good predictions on data which were not included in the fitting of the model. And you want to find correlations in your data which may tell you about some physics which you did not know about. Or you may find some correlations which are very interesting. So machine learning is normally, when we think of the statistical approach to it, is something which the statisticians would call a frequentist approach. It means, in few words, that we are less interested in finding a probability distribution, a PDF, which actually reproduces our data, or from which we can make an estimation. And we can say that A leads to B. So given A, we have a probability of finding B, certain probability. So the machine learning approach starts with the data, and you're less interested in finding a probability distribution. So it's a approach where the data is the one which drives your analysis, and the topics you're more interested in is actually to make predictions based on the model which are fit to data and to find correlations among your data. So I'm bringing this up because I want you to have that in mind when we are moving through these 2 weeks together. So predictions and correlations, and from a statistical point of view, it's a frequentist approach. By the way, all the links which you see here in the slides are links which you can click on, and they will lead you to the different websites which give you, if you want to deepen some of the arguments and you want to look up more definitions, which we won't have time to discuss during the lectures, I mean, please feel free to go through them. There's another thing which we need to keep in mind, and that's actually what is a model. And as you will see in these lectures, we are trying to fit some data to a model. It could be a straight line. So if we now jump into one of our first Jupyter notebooks, so a typical model, so this is taken from the same introductory slides, but now I'm looking at the Jupyter notebook. And as you could see from the polls here, I mean, basically all of you are pretty familiar. It's only 10% who are not familiar with Jupyter notebooks. So this is an example of a data set. It's a vanilla case. So I'm using this library called package, which is called scikit-learn. And I'm importing a linear regression. Later, we will see how to write our own linear regression code. What I'm doing now is, so scikit-learn actually wants to have the data in as matrices. So I'm not making a one-dimensional, but I'm making a 100 points times 1. So this is input then to scikit-learn. So I'm calling this linear regression function. And then I simply fit all my data points. So these are random numbers between 0 and 1. So this is a standard random number, a uniform distribution. And then I produce some data now. This is y. So I have the x's, and there's a relationship between x and y. And then I make a fit. And with that fit, I obtain the optimal parameters or the estimators of the model. And then I can make a prediction here. So my prediction is now based on this function. So using scikit-learn is pretty similar, pretty simple. So I would have a linear regression, there's a fit function, and there's a prediction function. Later on, we are going to make this a little bit more complicated. But you see now, my data now are the circles here, the red circles. And clearly, since I have this random noise here, I mean, this fit doesn't look very impressive. So if I was going to say that my model now is a straight line, which is going to go through the data, I mean, you would probably not buy my model. You would say, this guy Morten, I mean, he's trying to cheat me. So if I, on the other hand, if I make my random noise much smaller, so suppose I just multiply it with 0.01 here. So what happens then? Now it looks much better. So in a certain sense now, a model here where I simply have a straight line 2 times x with a very, very small noise. This is something which we would expect to be well fitted by a straight line. Now, if I go back and increase the noise again, I could obviously make a model here where I could traverse all the points. So I could now have I could try a polynomial fit, which would not be a very good thing. But if I use decision trees, I could actually traverse all the points here. On the other hand, if I do that, and if I use that to train, if I use all points to train it, I would end into something which leads to overfitting, because if I would have an outlier which was not in the training data, then my model, which I've been training, would fit badly the data. So coming back to this discussion which we had now about the model, there's and this is one of the big tasks actually. So to make the model inference well posed, that means to guarantee that there is a unique optimal model for the data, you need to have lots of additional assumptions. And in general, this is a very, very elusive task, or almost an impossible task. So what kind of model should we use? I mean, how do we gauge whether this is a good model or not? The most popular strategy which we end up with is normally to start with the simplest class of models and then increase the complexity of the model. Only when the simpler models become inadequate. So if you work with a regression point to fit a set of sample points, you might first try the simplest class of models, linear model. And then you would follow by using more complex models, like this small case which I showed you now. So going a little bit back to the slide here, I want you to keep this in mind, because to infer the correct model for a given data set is an elusive, if not impossible task. The fundamental difficulty is that we are not specific about what we mean. If we are not specific about what we mean by a correct model, there could be easily many different models that fit the given data set equally well. And this is often the difficult part. That's where your insights about the physics, about the signs of a specific situation you're encountering, where that really matters. So maybe we could take, so if somebody has some questions now, while I'm just going on here, if there's something which is a little bit unclear to people, I mean, please feel free to ask questions.
Yeah, I have a question.
Yeah, go ahead, please.
So I kind of get the idea of what the content of the course, but I guess maybe we go into that later on. But the exercises and the option for a project, could you maybe elaborate on that?
Yeah. So the for the exercises, we are presenting some exercises every day which you could look into. So we are going to have some questions and answers. We have a small break of an hour, and then there's going to be a questions and answer sessions, which starts at the 5 o'clock Central European time. And you should feel free to participate or not. So if you don't want to, I mean, you can work on the exercises. On Thursday, we're going to start with data which are relevant for the nuclear physics experiments we want to discuss. So we will have small exercises throughout the 2 weeks. So where you will get some hands-on practice on the things which we've been teaching about. But then, for those of you who would like to have credits for the course, and if your university accepts the credits, so in Europe this is pretty simple, because we have the European credit transfer system. And this course gives you 5 credits upon completion of a project, which you can define together with us. Or maybe you have some data set from nuclear physics you would actually like to analyze with the material we are going to present during these 2 weeks. There's obviously a limit to how much we can do in these 2 weeks, and with 2 hours per day only. So, and you can hand this in at a later stage. So we could fix a deadline, let's say in the beginning of September. If you are Master of Science students in Europe, you would have a grade between A and E, and F for failed. And if you're PhD students, is normally passed, not passed. So this is something which we can agree upon after we've gone through the course. And if you have some specific data sets already now, which you would like to analyze and perhaps write a small report, then the University of Trento, which is linked up with the European Center of Theoretical Physics, is the one which is going to issue a certificate and stating that this corresponds to 5 ECTS. So that's the same as 2.5 credits in the US. In the US, it's a little bit more difficult to have this approved because at universities you have to pay for credits, whereas in Europe, I mean, you normally don't pay for credits. Did that help?
Yes, thank you.
So if you have ideas for projects, or if you would like us to propose some of the projects and you would like to have credits from this course, then please feel free to let us know. Just send us an email, the teaching team. And else, you can get a certificate that you have attended the course. But that doesn't carry any credits with it. Any more questions? Okay, I'm going to move on a little bit. In the slides here, there are some practicalities on programming languages and aspects and some specific Python topics. And the in Python, we are going to use libraries like NumPy, numerical Python. There's another library which is called Pandas, which you will find extremely useful. And then we have these machine learning libraries like scikit-learn, TensorFlow, and PyTorch, and so on. If you're more familiar with C++ or Fortran, you can actually write things in Python and in Fortran and C++, but that's going to take a little bit more time. So the material we are going to provide is essentially Python-based codes using Jupyter notebooks. And then we are going to run many of these examples and show you how you can use both scikit-learn and TensorFlow. We will not use PyTorch, but if you're familiar with PyTorch, feel free to use that instead of TensorFlow. TensorFlow has now lots of functionality. Scikit-learn does not have much on neural networks and deep learning. So it has a simple feed-forward neural network. Whereas TensorFlow is the library which has things like convolutional neural networks, reinforced recurrent neural networks, and much more. And that's normally the library which people end up using. Or you could use PyTorch if you're more familiar with that. So some of you are familiar with statistical software like R. So there are many machine learning algorithms which are actually written in R. R is a very good library, or a programming language actually. That's wrong to call it a library. It's a programming language. And you, if you're familiar with R, you could actually use R. But in the lectures here, we're going to stay with Python. So in the slides here, you will find some introduction to Python. And if you're not familiar with it, you can install it. So I'm not going to spend time on this now because I would rather like to jump into some of the more machine learning specific terms. So I'm assuming now that you can skim through some of this material. There is material on how to handle arrays and so on. So if I go up a little bit in this Jupyter notebook, you will see several examples here on how to use NumPy in connection with vectors and matrices and in general arrays. And it's normal to just import numerical Python as an NP. And NumPy has wrapper codes to popular linear algebra libraries like LAPACK and many other libraries. And it's the code is highly vectorized. So it means that when you diagonalize a matrix using NumPy, you will have the same speed, or more or less the same speed as you would have if you were to run it in C++ or Fortran, or any of your low-level programming languages. So I invite you to take a look at some of this material. There's also, if you go back a little bit, I highly recommend a textbook. So if you want to get started and if you feel a little bit rusty about Python, if you move into the literature here, I've actually placed many textbooks. Don't tell that to the publishers. But there's a textbook here on Python for data analysis. This textbook is actually pretty good. And it starts with some of the basic numerical Python. It has pandas, it has reading, writing from file, and much more of the Python material which is relevant for data analysis and what we are doing here. So you don't need to go to chapter 30 to find the interesting stuff. So this textbook actually brings you up to speed pretty quickly. And I would typically recommend that one. Now, if we now go back to some of these NumPy, as I said, I'm going to simply ask you guys to go through some of the material, or you can watch the videos, which we are going to place online a little bit later. There's a lot about matrices in Python, and these are things which become important for us when we are going to construct the way we read and handle the data and feed that into a machine learning algorithm. What you will also find are topics like a brief reminder of statistics. And I'm going to use this now very quickly just to bring you guys up to speed a little bit, because this is now, as I'm going to move away a little bit, move ahead a little bit, I'm going to skip these quantities which you see here. And I wanted to give you a quick reminder of some of the statistical analysis elements which are important when you're doing machine learning. So when you've taken a course in statistics, you've often been introduced to the probability distribution function. So it means that if you think of our input data, the X's and the Y's, which we are going to use to construct a model in a machine learning algorithm, you could think of these as being results from some kind of stochastic event, that there is a probability distribution which governs them. Like you saw the data which we were making in that simple example, we had the X's which were given by uniform distribution and the Y's which were related to the uniform distribution, plus that we had a normal distributed noise. In that case, we know what the distribution looks like. Now, in machine learning, we are often not interested in the distribution. So it means that quantities like a moment like this, so if you know the probability distribution, you can actually calculate the exact moment. It means you can calculate, for instance, the mean value. Now, when we are going to estimate or gauge the quality of a given model, we will often then not have this probability distribution P of X. We may not even be interested in it because we want to fit a model. So the data which we have, they may be generated by some kind of obscure probability distribution, but we care less about that part. We want to make predictions and we want to find correlations in the data. We are less interested in estimations and causations. So it means that when we have a sample of data, so this is the ideal what you see here, if you have a continuous distribution. If you have a discrete distribution, this is just a sum over all the possible event X which you have dictated by a certain probability distribution. Now, in our case, we will never be able to get the exact mu. And then the question is, I mean, how far are we from this mu? So the other quantities which we are going to meet are like central moments. And one of the very, very important central moments is the variance. So which in case if we have the probability distribution which governs the stochastic events, then we know that the variance is given by the expectation value of X squared. And now I'm using this a little bit nasty physicist notation for expectation values. So I'm not putting an E, an uppercase E, which you would typically see in mathematics and statistics textbooks. And then this defines the square root, defines the standard deviation. And that's the spread from the mean value. Now, there's another quantity which is very important, and that's the covariance of two stochastic events. And that covariance, that measures actually the degree of correlations between two stochastic events. So an xi and xj. And if these are independent and identically distributed, they can actually be only, they need only to be independent. But if they're also independent and identically distributed, then the covariance would typically be exactly equal to 0 when xi or I is different from j. And that means that, so the covariance, when you write it out, is actually given by the expectation value of xi times xj minus the product of their mean values. Now, if these are identically independent distributed events or independent events, the covariance would be equal to 0. Now, the covariance is a quantity which is very interesting for us because that tells us about the degrees of correlations in the data set. And we are going to see an example a little bit later on a simple example on the correlations among data sets and how we can actually obtain that using libraries like scikit-learn or numerical Python and NumPy. So the covariance is a very important quantity. And if we move on a little bit, what you will see is now, so I'm just going to skip some of these. So what we have to deal with is not the possibility to calculate the exact mean or the exact variance or the exact covariance, because we don't have the probability distribution. So what we would have is the sample mean and the sample variance and the sample covariance. And these quantities need not be equal to the exact mean value or the exact variance. So suppose somebody also told you that these numbers are generated by a Gaussian distribution with a specific mean value and a specific variance, then you know that you should actually approach the exact value. But normally, when we have a model and then we look at our data, we may not be able to assess properly whether we have the correct variance or the correct mean value. And that leads to a very important aspect in machine learning algorithms, which is called resampling techniques. And some of these resampling techniques, like cross-validations, is something we're going to encounter in the beginning tomorrow. So we won't have the time today, but we're going to scratch the surface a little bit today. And another very, very famous technique is the so-called bootstrap technique. That's another resampling technique where you actually try to improve your assessment of the variance and the mean value by resampling among the same data set. So a typical situation you have is that suppose you run an experiment and this experiment produces something like 100 data points. So somebody like Sean, one of our other teachers, or Danielle, they may have run this experiment for a week, and there is no way, unless they are very, very close to Nobel Prize, where they can go back to the physics advisory committee and say that, hey, we need some more 100 data points and we would like to run this another week. Most likely the physics advisory committee would say, you have to be happy with what you have. And these 100 data points are then often used together with this kind of resampling techniques. So in many cases, we would have few data points. In other fields, on the other hand, we would have tons of data points. That depends from case to case, and we are coming back to that. But we want to have you to keep in mind that we are taking a frequentist approach, and the quantities which we are actually calculating are the sample means, the sample variance. We are looking at the covariance between two events in order to find correlations in a data set. So this covariance is often used to define something which is called a covariance matrix, which then, if you divide it by the variance, leads to something which is called the correlation matrix. And that's a quantity which is widely used in the machine learning community in order to find information about correlations in your data set. So if we now just summarize a little bit about the statistical aspects, so the quantities which we will be dealing with would be the sample mean, the sample variance, and the sample covariance. So these are the statistical elements which you will encounter again and again in machine learning algorithms. So what I want to do now is to go back to a simpler model. And we are going to look at some specific examples on how we can compute some of these quantities using a library like scikit-learn. But before we do that, and before we take a break, I wanted to introduce another Python package, which you will find extremely useful. And this is called the pandas, which actually stands for, is a package which stands for panel data. And it's a very efficient library for data analysis with an emphasis on tabular data. So there are two major classes. One is called data frame with two-dimensional data objects and tabular data. And in the examples below, we're actually going to show you how we can use that to make our first nuclear physics example, which is to fit the nuclear binding energies. That's a kind of evergreen in nuclear physics. And then it has another one, which is called series, with a focus on one-dimensional data objects. The thing with pandas, which makes it so versatile, is that it allows you easily to read in data from various file formats. So this can be a comma-separated file, it can be an HDF5 format, it can be a fixed format file, and so on. And then you can reshape your data easily into columns and rows. So here's just a simple example, which also tells you what kind of movies I love to watch. So I can now make a data set here where so I would typically import pandas as PD. And then, so I have a first name, last name, place of birth. And then when I display it, if I run this one, you see now that what I produce now is an index here. And then I have the first names, the last name, place of birth, and date of birth. And then what I've done here now is simply to produce, this actually looks like a matrix, right? So in our case, this is a 4x4 matrix, and I have the indices here. Now, if you don't like these indices, 0, 1, 2, and 3, you can actually change one. So I just change that, the index here, as you see in this line here. So I just change that one so that I can actually put their names in front here. So I change this 0, 1, 2, 3, and I just named it differently. And this is a very efficient way of actually setting up your data. You can pick one specific if you want to. You can, and then you get all the data about it. It tells you what kind of data type it is, the name of the data type. You can easily add new data. So you would simply have a PD data frame, new Hobbit, and then you add a new index here. So you just write append, and then you can add a new one. And that means that it's easy to add, take away data, and so forth. And you see now I've added a new Hobbit, actually. And you can continue like that. It's very easy to set up matrices and handle them. So in this function here, I'm setting up a 10 times 5 matrix, 10 rows and 5 columns. And I do that by setting up random numbers. So this is rand n, it's a normal distribution. I define my data frame to be this matrix A, specified by rows and columns. I can calculate, if I do the mean here, I can actually, so pandas has a possibility to calculate the mean. So what I can do now is actually to calculate the mean value of each column. I can do the standard deviation of each column. I can just square it. I can do mathematical operations and so on. This is extremely useful because one of the things we're going to meet a little bit later is the normalization of your data. So sometimes for many of these algorithms, you may have outliers in your data. And you would like to reduce the emphasis on these outliers. So you would typically scale your data or renormalize your data. And one of the things you would do then is typically to normalize your data by subtracting away the mean value. So you could actually write df is equal to df minus df mean, just to give you an example. So if you run this one, what you would see now is this is your matrix which we had, and the numbers which you would see here would be the mean values for each column. The next one would be the standard deviation for each column. This is now my squared matrix, and so on and so on. So you have tons of applications you can actually perform on your data set. And you see now that instead of you writing a function which does all this, you have basically just a line here. So you just write df squared, and then you just square the matrix elements. So that gives you very compact code, and it's much easier to read for somebody who actually wants to peep into your program. I just added some more functionality here. There is a Python or package which is called Seaborn, which is a very nice way of displaying data. We are coming back to that one. I'm not going to run through everything here. But the the thing which we looked at right now was this simple example here of using scikit-learn. And in scikit-learn here, before we write our own functions, what we need to do is to have the x values in terms of a matrix. So we have only, it's simply just x here. So it's a matrix of dimensionality 100 times 1. And the same with the output y. So these y's are normally called the outputs, or the target values, which we want to reproduce. And this is a simple example where we combine scikit-learn. We make a fit of a straight line, so linear regression. And then we make our prediction. So our prediction here is this straight line. Another question is, how can we actually assess the quality of this fit which we made? Is there a way we can use? So let's say a little bit about that before we take a small break now. So I'm going to go down a little bit. And one of the quantities we will encounter is something which we call the cost function or the loss function. So after the break, when we are going to derive the equations for linear regressions, this is the quantity which we want to minimize. So one of the quantities we could define as a way to gauge how big the error for a single training example is to look at the relative error. So these are actually vectors now. So this is your data, y. The y tilde is your model. And what I have here is just the vector y here. And this is basically the relative error. Now, one of the reasons why this quantity is not that much used is that the derivative of this one is a discontinuous function. So when we are setting up algorithms for optimizing the parameters of the model, we would like to have derivatives which are continuous functions. But you see now you can easily here rerun this case. And then, so I have a slightly different example here. So I have 5 times x plus some small stochastic noise, which is normally distributed. And then I calculate my mean, my relative error. So I take the absolute value, my prediction minus y, and divide by the value of y. You have to be a little bit careful here, so y isn't 0. But in this case, when you run it and you make a plot, you see this could be one possible way to gauge your error of your model. So you see now that this is pretty okay. If I obviously reduce my noise here, then the error is going to be smaller and smaller. So if I do that, you see basically now I have an outlier here, and essentially my error is close to 0 here. Now, scikit-learn has this kind of functionality baked in. And you will see now in this statement here, like with the scikit-learn metrics, so we can compute the mean squared error. And this is the quantity which we normally use to derive the equations for linear regression. There's something which is called the R2 score. There's a mean squared log error, mean absolute error. There are many ways by which you can actually gauge the quality of your data. And you can also find the coefficients of your linear regression. You can find the intercept, as you see here, and then you can find the coefficient. You can make your models obviously more and more advanced. And these quantities are actually described here. So the mean squared error, it measures the deviation between your model and your data. It's pretty close to something which looks like your variance. And this is the standard quantity which is used to actually derive the algorithm for linear regression. Another quantity which is often used is the R2 score. So we're still talking about fitting a function. And ideally, this one, if everything is perfect, this should be equal to 1. There are other quantities like the mean absolute error, something which is called the mean squared logarithmic error, and so on. There are other types of functions which are used to find your optimal parameters for the model. So something which is called the Huber cost function, which is actually very popular. especially if you have data with many outliers, and so on. We are going to focus now and on the mean squared error. This is going to be the quantity, the mathematical quantity, which we're going to use to derive our first machine learning algorithm, which is linear regression and ordinary least squares. After the break, so we need a small break now. I mean, at least I need a small break, and you guys need to wake up a little bit. We are going to look at our first encounter of machine learning algorithms. Just linear regression ends up with us having a mathematical equation where we simply need to invert a matrix. That's the basics of linear regression. Now, when we do logistic regression, which is normally used for classification, so these are examples of supervised learning methods. In logistic regression, we will end up with a set of equations which are going to be non-linear in the unknown estimators or parameters, as we're going to call them. But let's remind ourselves of an evergreen in nuclear physics. So we are going to look at fitting nuclear binding energies. So let's just remind ourselves of some of the basic steps here. The binding energies, there's a mass evaluation from 2016. So if you click on this link here, you will actually find the table where you have all the data on 3,437 nuclei. And what you see here are just standard definitions of many of the basic parameters. And the binding energy is simply given by the number of protons times the mass of the hydrogen, mass of the neutron times the number of neutrons, minus what's normally called the mass here. And the binding energy, which we normally look at in standard textbooks, are typically fitted by what's called the liquid drop model. And in the liquid drop model, we would have a term, which is normally called the volume term. And you can see the definitions in the slides here. There is a term which is the surface term, and that goes like the number of nucleons to the power of 2/3. There is a Coulomb energy term, which goes like 1 to A, the number of nucleons to the power of 1/3. There is an asymmetry term, and you can keep adding terms. But what you see here now is something which looks pretty much like a polynomial fit. So there's a polynomial in terms of A. So the data comes as function of the number of neutrons and the number of protons. And then based on our physics intuition, we are now proposing a model which is meant to fit the data. So this is the kind of basic steps which we discussed in a more generic way before the break. And before the break, we said that one of the elements in machine learning is you having the data, you have a model, and then you need to have a way to assess whether this model is a good one or not. So one of the first things we need to do is actually to read in our data. Now, this data, if you now go back to the GitHub address of where you find all the relevant material, so you can use this material as you want. If you do a git clone or download here, you will actually have everything on your laptop or PC. And if you're familiar with Git as a version control software, then you know that writing git pull, either in a terminal window or git pull in a desktop graphical user interface, you can pull down and have the latest version of the slides. And this is the way we are actually going to develop this material. So you will probably see that we don't have all the material for all days. So this is going to be added almost day by day. So if you early in the morning, if you just do a git pull, you will most likely then find the latest versions of the slides and the teaching material. But if you go into this doc folder, and in this pop folder. There's to day one, or the introduction, as you see here. If you go into the Jupyter Notebook, this is where the Jupyter Notebooks resides. Then there's a data file here. There's a folder. And this folder has the mass evaluation data, which I just pulled down from the website, which you saw previously. And in here, you will now see the data. So this is the output of a Fortran file. And you can see now this is the way the output looks like. And sometimes you just watch this file and say, hey, I mean, I don't want to write a program which just reads in this data in a specific way. Is there a way I can do this in the simplest possible way? And this is where pandas, which we discussed before the break, comes in. So pandas allows us actually to extract the information we are interested in. So there is a column with a binding energy. There's a column, as you see here, with the number of neutrons, the number of protons, the number of A. There's also the element number. So maybe we are just interested in some few of these because we want to make a fit. And in the model which we have decided to look at, the fit now depends only on A. We could make this a little bit more sophisticated, and we could add N and Z if we want to, but let's try to keep this as simple as possible. And the what we need now is, so what I provide in the lectures here is a function which just sets up some of the basic packages which we need, NumPy and pandas, matplotlib for plotting, and then I have scikit-learn, which I import as SKL, as you see here, just a shorthand. There is a function in scikit-learn which is extremely useful, which is train test split. And you will find that very useful a bit later. Now we are going to be a little bit more brute force-like. So we're going to use all the data to train the model. So we're not going to leave data as test data on which we want to make predictions. Okay, so what I have here is now a function which allows me also to plot my files and save them. So you will see that, save fig. I define a data path. So I like to structure things in terms of folders. You can see there's a results folder, there's a figure files, there's a data files, and then the file which I'm looking at now is the mass evaluation. So if I run that one, then I'm having the read in the data file. And then the problem with our file is that this comes in a formatted way. And that can sometimes be a little bit, how to say, a small pain when we want to rewrite our data. So in this specific case, the data have a specific format. So this is a formatted file. It's not a comma separated values. And the in our case, we need to actually peep into this file. This is normally something which I always recommend. Look at your data files. And pandas has now a function which calls this formatted file, FWF. I want only to use some specific columns. So I use the columns 2, 3, 4, 5, 4, 6, and 11. So that means I want to use a column which has the neutron number, the proton number, number of nucleons, the element name, and the binding energy. But I need to specify the widths here because this is a formatted file. So that's the kind of detective work which I have to do before I start doing anything. So the preparation, everything is in here, but then everything, the rest is very, very easy to look at. So for instance, now what I'm doing, I'm just converting everything to numerics. I'm dropping cases where there's not a number. In some cases, you will actually see that the data files which you're looking at, they do have errors because there's a human who punched in a data point, a data entry. And that data entry could have been punched in the wrong way. Now, in this case, everything is generated by a Fortran file, but there are cases where there is no data. So you would typically drop that. And then, so what I've done now, I have the masses, define this is a column with binding energies. That's the only one which is dealing with. And then I want to turn everything into mega electron volts. So I divide by 1,000. The data comes in kilo electron volts. Then there's another functionality in scikit-learn. And in this specific case, you would just group by A, because now I want to fit a polynomial by just using A. Now, there's a question here if there is a specific way to determine the data structure of a particular data file. I am not aware of that, but if somebody is, there's a question from Craig here in the chat box, so feel free to answer. So the comma-separated values is a very easy one. Yeah. In our case, we actually have to look at the format because this is a formatted file. Then this allows us to actually manipulate the data without having to write tons of functions which does it. I mean, when you've written such a function once, there is no new insight in actually writing a new one for the specific data. So that means that having all this functionality means that this saves us a lot of time. So let's run that one. And now we have defined that. So the next thing I'm doing now is to just define an array, which contains the values of A's, the values of Z, the values of N, the element names, and so on. And I've picked only those which exhibits the largest binding energy. So I'm not fitting this to everything. It means that what I'm getting now, and I'm just printing out parts of it, is I'm just getting 267 data points. And I have 5 columns because I have the masses, now the A values, the Z values, the N, element name, and energies. So I have a question. So yeah, the widths here. So there's a question about the widths here. Now, if you now look at the data file itself, so this is the way when you spit out from a Fortran file, you specify that this one has a width of 1 character. So if I say the width is 3, then you have 3 characters, so there could be empty spaces. If you look at like these binding energies, this has a number of, so the width of this one could be something like 8 characters, which define that one. So that would be the width. So you actually have to go into the data file, but you will also see now that the authors of this data set, they've actually specified. So A is actually old-fashioned Fortran. It says it's a character. So I is an integer with 3 spaces. Here you have 5 spaces and so on. So you actually have to look at the way so F is a float. So it has 11 spaces, or 11, you can have 11 numbers, and you have 0.5. So that means that you have 5 numbers after the decimal point. So this is not in scientific notation. If you want a scientific notation, you will have an E here. So let's, what we did now was simply you see that in these with these very few commands here, you can actually read in the file, and then you can reorganize things, and then just spit out these different parameters which you want. So masses is the common denominator, and no, that file would also not read a table, unfortunately. Yeah. I think the hashtag means that there's no data. I think I have to remember what it does. Yeah, I'm not sure what this hashtag means. I have to look it up. Yeah, it's an extrapolated value. Thanks. This is fantastic. Thanks, folks. Yeah, what it means in it. Yeah, I think I need, yeah. Okay. Yeah, in place of, yeah, extrapolated values. That's correct. Thanks. Okay. So the next thing we are going to do now is to design or set up the design matrix, or what's normally called the feature matrix. And this leads us now to the basic mathematics of linear regression. And what we need now is to set up a matrix. And if you look at this matrix is going to have 5 features. And the features go back to the model which we opted for. So if you look at the model, there's going to be an intercept. And then there is going to be the next term, which goes like a to the power of 1, which is a volume term. There's a Coulomb term. There is the surface term, there's a Coulomb term, and then there's the asymmetry term. So if I add the intercept, I have 5 features. So I'm trying to fit a polynomial now with 5 types of features. So it's not a straight polynomial which goes like intercept plus x, x squared, x cubed, and x to the power of 4. So if we go down again, what I'm doing here now is actually to set up a matrix where in the first column I simply have something which is related to the intercept. In the second column, so in the rows, I have the values of the energies, these values which you see here. And then I'm now setting up the polynomial fit which I want to do. So this, what I'm doing here now, is my first encounter with us setting up the data which enters the machine learning algorithm. So you may perhaps think this looks a little bit strange, but actually this is one of the easiest cases we can do. So I'm actually going to call this a kind of vanilla case. It's a vanilla case because it's pretty simple to set up the so-called design matrix. So we are going now, in order to find the optimal parameters, we are going to have to invert the transpose of this matrix times itself. And then we will have an analytical expression for the parameters of the model. So still some black magic. Now I call my linear regression. I transfer this matrix, and then I have my targets. These are the y values, which we called them previously. And these are my energies, which I now want to fit. And this fit y is my prediction. So there's a question here, what is the difference between using a direct polynomial fit and linear regression with several features? Actually, this is much the same. And I'm coming back to this now because some of you are impatient to understand what the design matrix is, because I haven't given you any mathematics yet. And this is coming now. So if you just give me 5 minutes, because now I wanted to show you the functionality here. So if you, for the moment, just accept that this is a kind of black box which we are using. And then we need to go back to this design matrix so you understand better the mathematics. So I hope you can just wait a little bit till we get there. But this is a question from the chat. So please feel free to add these questions to the chat. And if you see that I'm not answering and somebody has the answer, please feel free to answer, because that works extremely well. Yeah, this is another thing, partial pivoting. That's a technicality which I'm coming back to, because when I'm making a polynomial fit like this, I can actually use a basic matrix inversion algorithm without thinking of having a determinant which is 0. And that's mainly when you have a polynomial fit, every column will correspond to an orthogonal polynomial. And that means that the columns will be linearly, the solutions will represent linearly independent vectors. And that means that normally when you have a problem like this one, the solution of the problem is a trivial one from a numerical mathematics point of view. So I'm coming back to what this design matrix, why it looks like as it does, because this contains a lot of the problems which we are going to meet later. And hopefully you will see that when we spell out the mathematics of linear regression. Now, the way we do it in scikit-learn, if we don't want to write our own code, actually what you need to do is just invert a matrix. Then I'm just calling scikit-learn. Oops, I forgot. Did I forget to? I must have forgotten to call something up here. Let's see. Okay, so now I did a fit and I made a prediction here. So the next thing I want to do now is actually to plot the results. And you see now how easy it is to plot my results. So this gives me also the mean squared error. The mean squared error is ideally, I would like to have that one equal to 0. And the variance score, the R2 score, has an ideal value of 1. This is not that bad. I can also calculate the mean absolute error. And these are the parameters which we have in front of the polynomial. So this would be my intercept. And so I had a polynomial of degree of 5 elements. And these would be the coefficients in front of each of these elements. And the fit here, when I look at it like this, it looks decent. What I also wanted to give you now, before we move on, is how we could use another algorithm. So these are called decision trees. And in scikit-learn, a decision tree for regression, so fitting a function, is simply called by importing decision tree regressor. And I can make these trees as deep as I want. That means it can have more and more complexity. So if I have a tree of depth 9, it means that I'm almost reproducing every single point. And when I run it, you can now see that with a depth of 9, you suddenly see now that I have an almost bang-on prediction of my data points. So my standard linear regression was not very impressive, not that impressive. Whereas with the decision trees, I can actually fine-tune it so that the prediction, which is the average values of the data points in a specific region, is as close as possible to the value which I want. Sometimes you will see that the prediction has equal values. So it means that it has actually placed these numbers here and then makes a prediction which is a little bit farther away from the actual value. So I can tune these decision trees. So if I were to make a depth of a tree, and we are coming back to, yeah, this is a good question. When I'm fitting a regression tree, what you basically do is that you divide your data points in squares. And then you could say the deeper you make the tree, the less data points you have in a square. And the prediction you have is the mean value of the data points in the square of your region of data. And you can make this tree finer and finer so that you reproduce every single point. That leads to something which some of you have been asked about overfitting. So this really leads to overfitting, because if you have a point then which is not in the training, you will not be able to reproduce that point. And we are coming back to that. That's a very important issue. So I haven't mentioned that yet, of overfitting. And the depth of the tree is by trial and error. So we are going to look at this a little bit later tomorrow when we discuss the bias-variance trade-off, because that becomes extremely important when we want to find out how complex a model is. So recall what we discussed previously about the complexity of the model. So we can have a simple model, which normally will give us a larger error. So like the mean squared error would be larger than. We can make the model more and more complex till we reach a point where we are almost have a mean squared error, which is close to 0. And then suddenly, when we make the model a bit more complex, we are entering the region of overfitting. And then the mean squared error starts increasing on data which was not included in the fit. So if I now run this with 11, so I make my tree deeper and deeper, what you will see then is that suddenly there's a perfect match with basically all the points which I just printed out here. So if I make it shallower and shallower, so suppose now that my last one, which is the one I print, I make that one equal to 3 here, then you will see a case where you see now that the expectation value is the mean value of all the possible data points in a square. And then this is the expectation value which the decision tree actually reproduces for you. And then the results are a little bit worse, obviously. So you can actually tune this, but we are going to look at how we can tune this in a proper way a little bit later. Now at the end here, there's also an example on how to use neural networks, but we are going to skip that one because now I wanted to move into linear regression and the mathematics of linear regression so that we can see how we actually define these quantity which we call the design matrix and where it comes from. Now, the difference between fitting and prediction. So when you split your data into train and test, so you train the model towards a specific set of data. That's the fitting. So when we typically say fitting, we have taken a set of the data, let's say 80%. We could have picked these data points randomly, and then we fit a given model. So this could be a 10th-order polynomial, just to give you an example. Then we obtain the parameters of the model. And when we have the parameters of the model, then we make a prediction on data which was not included in the model. Sorry, in the fitting or training. So fitting / training, they're going to be synonymous words. And prediction testing are going to be to have the same meaning. So I'm going to change between testing prediction and fitting training. The kind of percent of data which you would have in a test and train is normally something which there's no specific rule for that. So they often runs from 70% to 80% in the training and 30-20% in the test, but it depends very much on how much data you have. So it all depends on the quality of the data, the amount of data you have. So if you have tons of data, then you could easily use some 80% on training and 20% of fitting. If you have less data, you may actually think of using less data on training. Okay. Yeah. So to resolve the overfitting problem, that's one of the holy grails of machine learning. And we are coming back to that one. And you're going to hear that again and again. So tomorrow we're going to discuss about the bias-variance trade-off. And that's where we're going to discuss a little bit more about these topics like the overfitting. So the example which I had here was a simple vanilla case. And we took all the data to fit. And we are going to change that when we now move into a little bit more serious cases. So let's move in back to linear regressions and look at the linear regression slides. So we can take a look at the mathematics there. So now we go into the linear regression slides. And what we need to look at now is the mathematics. So in here, in this set of slides, and this is going to migrate a little bit into tomorrow as well. So we will probably sneak some of this material in these slides for tomorrow's lectures as well. So we are going to look at specific linear regression methods. So we'll focus on ordinary least squares, ordinary linear regression, ridge regression, lasso regression. We are going to look at resampling techniques because often we don't have that much data. And then we are going to discuss this bias-variance trade-off, which becomes important when we now want to have a kind of handle on overfitting. So these are all intimately linked topics. And now you may ask, why do we put linear regression into machine learning? Because linear regression, the standard ordinary least squares, is nothing but a standard application of linear algebra, where at the end we need to invert a matrix. So this sounds like a kind of overkill in particular in connection with something like machine learning, because the algorithm is very deterministic. We can derive this from a statistical point of view if we take a normal multivariate distribution and take the derivative of that one. Then we're actually going to get the same expressions for the unknown parameters. But let's now look at the mathematics here and why we actually find linear regression so interesting. So we are going to make a model in terms of a parameter beta. So this is the unknown parameter. In statistics, this is also, you would find this being named an estimator. Then it's a method of choice, fitting a continuous function. And this has been around since the 19th century. It came around roughly around 1850. So it's been one of the methods of choice for fitting a continuous function. It gives an excellent introduction to central machine learning features. And it has what I would call understandable pedagogical links, because when we come to neural networks, it's much more difficult to extract a clear mathematical connection between the parameters and the final model which we end up with. There's an analytical expression for the parameters, beta, and that's pretty seldom that we have something like that. We have something else, which is also very interesting. So when we deal with a frequentist approach, what we can do then, if we can calculate variances, is that we can provide confidence intervals. And the specific thing with ordinary least squares or ridge regression is that we have analytical expressions for these quantities. That's pretty neat. We also have analytical relations with probabilistic interpretations. We can easily introduce concepts like the bias-variance trade-off and these resampling techniques, which allows us to, and you will see that tomorrow, this allows us to actually run simple cases where we can illustrate things like this bias-variance trade-off. And it's easy to code, just a few lines of code. And it links well with classification problems and logistic regression. And there's something else, because I said that in the previous lecture, at the heart of basically all the machine learning algorithms, we need to plug in a minimization algorithm. So if you want to develop your own gradient descent method, since you have analytical answers or analytical expressions for your unknown parameters, then this is extremely useful. And gradient descent methods or minimization and optimization methods, they're really at the heart of essentially all machine learning algorithms. Now, I also wanted to indicate there are some extremely useful texts. There's Wessel von Wieringer's article on ridge and lasso regression. Then we have, this is by Pankaj Mehta, and he and his colleagues, they wrote a review article, which is extremely useful. It's a physics reports paper, and it's a beautiful one because all the examples they have all examples there, they have a Jupyter notebook. So it means that you can actually pull down a Jupyter notebook and reproduce all the results which they have presented in the article. That's the way science should be done. Then we have the classic textbook by Hastie, Tibshirani, and Friedman, which is also a highly recommended text. So if you want to read more, please take a look at these things. Okay, so now let's dive into some of the mathematics here. Eh? So the regression analysis, definitions and aims, so that you can see where this design matrix, where it comes from. So what we would typically have is a set of variables X. These are normally called dependent, the outcome or the response, while the set of variables X is called the independent variable, the predictor variable, or the explanatory variable. So many names here, or feature variable. So what we are dealing after, so we would have n data sets. We have some responses or targets or outcomes, the variable Y. So if we are fitting, this could be our energies. These X's would now be the A values of the nuclei to a given power. So we would have some explanatory variables, which then could be the elements of a given polynomial. And then the goal of regression analysis is actually to exploit this relationship between Y and X in order to infer some dependencies and find correlations in your data. This matrix X is normally a matrix of dimensionality n, which is the number of data points we have, times p. So you could think of an example like this. Suppose you want to find out among 20,000 patients, which part of the DNA is responsible for a certain type of cancer. So your patients would be then, the 20,000 would be n. So you have 20,000 patients. So that means that if you go back here, n would be the cases, 20,000. Then if you look at the DNA, suppose now that there is 1 million of DNA features which you want to analyze. So P would be equal to 1 million. Now, in our nuclear physics binding energy cases, what we had was something like 200 plus nuclei. And then we had 5 features. I mean, we had the powers of A. So we had the volume term, the Coulomb term, the surface term, and the asymmetry term plus the intercept. So that gave us P equal to 5. If I'm doing this type of cancer research, P could be something like 1 million features, or as people call them, predictors. That's another name for it. And these data sets, they enter the definition of the design matrix. And then Y is the response. So in the case of cancer, it could be a benign tumor or a not benign tumor. So yes, no case. Or if we have a function, we would just have some continuous values. Y, in our case, would be discrete values. So there would be something like this, so a Y of I, and I'm suppressing this to indicate that now I'm picking out a specific X value I, and that links with Y here, a specific Y value. And then the assumption now is that there is a model which is linear in these unknown parameters beta, and these are normally called the regression parameters or estimators. So what we would have then, if we now go back to this case here, you see now that what I would have my nuclei. In total, I had something like 3,000. And then I have P equal to 5 here, 0, 1, 2, 3, 4. So there's 1 here, 1 here, 1 here, here, and here. So I have 5 predictors or features for setting up this design matrix. So my matrix could then be n times P or P times n, depending on how you want to set it up. So normally you would have it n times P. And if you go to another case, a very popular case, like there's a credit card data set, which is contained in many data sets, many repositories for data sets. In that case, you have 30,000 credit card holders. And then the predictors would be gender, age, profession, education, and so on. In total, there's something like 24 such predictors. They're also called attributes or features. So your matrix would then be 24 times 30,000. This is normally a classification problem because the outcome is you paying your credit card debt or not paying it. So that's a yes and no case. Whereas here, we are doing a regression case, and that means we are fitting the energies to a specific polynomial. So if you now look at the specific case here, I'm going to sneak in some 5 more minutes so we can set up the mathematics and we can start from that one tomorrow. So I hope you can forgive me. So let me just finish this one and then I'm going to take some questions afterwards, if that's okay. So what we are doing now is to set up a model where we have a y here, which now, what we are assuming is that our data can be reproduced by a model. That's the first part. So in linear regression, we are assuming now that there exists a function plus some noise. This noise is normally distributed. That's the assumption behind linear regression. So we have a normally distributed noise, and then we have some function here. So what I'm doing now is to say that my data are given by this model which I make, and here I have the unknown parameters. So if you're doing a polynomial expansion, this is what you would typically have. So this would be x to the power of j, and then I have some parameter in front here. So from the intercept to the different parameters. So if I then set everything up, what you see now is that I would have a y0. So that has an unknown parameter beta 0, unknown beta 1. x0 to the power of 1 is known. These are just my data points. x0 to the power of 2 is known, and so on. So it means that what I'm doing now is simply to set up something which is going to end up with a matrix times a vector expression. So we are going to skip the epsilons. So we assume that they are normally distributed. There's a normally distributed noise. So if you then define everything in terms of vectors, so you would have a vector y, you have a vector beta here, and now observe one thing. I have as many features as I have data points. And you know that if I have 2 points, I can fit a straight line. And then I have 2 unknown parameters. If I have 3 points, I can fit a second order polynomial. If I have 4 points, I can fit a cubic polynomial, which means 4 unknown. So in this case, P is actually equal to the number of data points which we have. And that means that I can write everything out in a compact way. So my design matrix looks like this now. So if you go back to the previous slide here, you see now that when beta 0, which is unknown, that yields 1. The next column is x0. So that means that what I'm doing now is to set up a model which is linear in the unknown parameter beta. So I have my matrix, which is known, my y here, which is known. We have those data points. And then I'm going to skip this epsilon because this is something we assume to be normally distributed. And now you see that if we go back to the nuclear binding energies, you would now see, if we go back to that, you see that my first column contains the 1s. The second column has a to the power of 1, but the second one does not, the third one does not have a to the power of 2, but to 2/3. So you can actually opt for the kind of model you want to have. And then you have to compare that with data afterwards and see if the fit is reasonable. So what you have now is your design matrix. And this is called a van der Molen matrix. It actually has its name in the literature. But you could make this, I mean, you don't need to have this to be just simple polynomials in X. These could be more complicated functions. You could have wavelets, you could have Fourier series, you could have cosines or sines or other types of orthogonal functions which you can plug in. So that means that basically your matrix would more look like this. So instead of having, like in the previous case where you have x0 to the power 1, x0 to the power of 2, and so on, you would now simply have some coefficients x00, x01, and so on, which then could represent these more complicated functions. And note that in this case, we put the number of features equal to n. So that means that the matrix is symmetric, and this is not generally the case. So this is your matrix. And now the question is, how do we actually obtain the optimal beta I values? So I'm just going to sneak in some 2-3 more minutes, and then we stop here, take a small break, and then we move on to the exercise sessions, which we will also do in Zoom. Somebody actually asked about that one. So the matrix, so let's just move on a little bit. And what we could do now, if we want to do the mathematics, is that we are going to assume now that we have a model which simply is this design matrix times beta. Then we define our cost function or loss function. So normally the loss function, people tend to define that as the individual contributions. So what I'm doing now is to define a function which I'm going to use as a measure for the quality of the results. So I take my square difference between the actual data points and the model. And I can rewrite this one in terms of the transpose of these two vectors times the difference between the two vectors. And if I now introduce this quantity here, you see that this will be the transpose of this matrix. So beta has dimensionality p. T, if I define T as a P times N, I need to take the transpose, as you see here. And that means that I need to take the transpose here as well. And this is my cost function. You will also see definitions like 1 divided by 2 by n, because when you take the derivative, you get rid of the factor of 2 here. But that's normally the standard definition is actually the one which you see up here, this definition here. So what I'm going to do next is simply to take the derivatives of this quantity with respect to beta. And if I take the derivatives with respect to beta, so if you move down a little bit, so this is the problem which we want to solve. And we want now to find the minimum of this cost function in terms of the parameters beta. So what I've defined now here, I just changed the X to be a matrix which is dimension n times p. Beta has dimension p, so that means that what I end up with then is a result here which has dimension, vector dimension n. I take the derivatives with respect to these parameters. So you can just follow the derivation here. It's actually not very difficult. And what happens then is that I find in a more compact matrix vector form, I have that the transpose of this matrix multiplied with the y minus my model is the quantity which I want to put to 0. And then things become pretty easy. And I end up with this equation here. I have x of t, x transpose times y. These are known quantities. I have x transpose times x. This is my design matrix. And then I multiply with beta. And then I invert that matrix. And there I have the parameters beta. So in the case which we have now, since this matrix here becomes a P times P matrix, and P is equal to 5, this is a small case. If you, on the other hand, look at this cancer case we mentioned, with suppose 1 million features, this will be a million times a million matrix. And that means that the domain of applicability of these types of methods are less relevant, because you would normally not be able to invert a matrix of 1 million by 1 million unless you have access to huge amounts of random access memory. So the typical cases you would end up solving is normally when P is much less than N. And for the nuclear binding energy data, which we will start with tomorrow, we actually end up with a 5 by 5 matrix to invert. And since we are doing a polynomial expansion, this normally is a case where we seldomly will have problems with the inversion of the matrix. But normally you would solve this with something we call singular value decomposition to find the inverse. That's the standard algorithm which is normally used. Or some partial pivoting to find the inverse of the matrix. So I'm going to stop here today. We're going to take a small break. There will probably be many questions now. And then tomorrow, we finalize linear regression in the first lecture. And then we move on to a discussion of logistic regression in the second lecture tomorrow. But we need a little bit more time.